How do you identify the stack corruption, right? There's a very old and well-known technique, which is called stack painting. So the basic idea is that, let's say that this is your memory, right? This is your memory, your stack pointer starts from here. It kind of grows in this direction. Your heap starts from here, like, and if you have any heap, if you are using any heap, it starts from here and it grows towards the stack pointer. So what you do on the boot up is that you're probably using just a few bytes. So as part of the reset handler, or bootloader, usually even before bootloader, so that you can even catch issues with the bootloader. You basically start, because at that point you haven't started using heap. Like you can almost think of there's like zero usage of heap because you are inside the reset handler. What you do is that you basically paint it. So I will actually paint it using blue color, but how you actually do it in the firmware is like you basically keep going up to the point where whatever is the stack pointer's value at that instance. Usually it has only used like a couple of integers. So it's usually like 12, 30, 64, depending on how much you have used it. So you basically paint it. And when I say paint, obviously you don't have paint. The idea is that you fill it with some magic number. I've used people use something like A5, 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 or even people use dead beef. So of course these are both have. So you start from here, you enter one entry of dead beef, another entry dead beef, all the way up to the whatever is your current value stack pointer. And the idea is that then you let your application run, and eventually at some point you either using like a CLI or console or some other thing which runs when all of your other threads are idle. It runs intermittently or periodically. What it does is that now this track, what it does is that it basically starts going through from here all the way up, and it basically sees that where the heap ends and where the and up to what point is do you still have these this magic number values in there. If you see that the heap ends over here, and you cannot find any magic number value, or basically and you don't find any magic number value after that, then it means that your stack has basically overflowed and it has basically touched the heap part. So it means that one of the thread or task or your application is basically using the full stack. So that usually is one way to know this. Of course, even with this one, there are ways where it doesn't cover all of the scenarios. So, and when does it not cover the scenario? It's one example is that, let's say that you have for some reason you have a thread, you have a task, and within that task you had a bug, and for whatever reason it wanted to use 4 KB of or 10 KB of 10 it allocated a 10 KB array, look like within that stack, on the stack, or it allocated not like not memory allocated, but it allocated like a local variable. Now the thing is that you would probably only use the first few bytes or the last few bytes, and most of the memory in there would be untouched, which means that most of the memory would stay as dead beef, especially if you don't initialize all of your variables. That's why they say that it's a really good idea to initialize all of your variables to null or zero. Because if you would have initialized your whole array to zero, what would happen is that um, you would see that all of those magic numbers got overridden. But the idea is that, let's say that it was a big array. I'm using red color over here. So yeah, so it was a big array. It was so big that it ran all the way from there to here. Like it was so big. but you only use these number of bytes, or you used to only use these number of bytes at the end or at the start, then when your stake paint check routine would run intermittently or periodically, it would basically see that, oh, all of this stuff over here, let me use green. Okay. All of the stuff which is in green, it corresponds to dead beef or whatever magic number you used. So it would say, oh yeah, life is good. There was no stack overflow, nothing actually used all of that space. So basically stack painting is one way to go about it, but it's not it doesn't address all of the ways. There's another one where you basically take advantage of something which is provided as GCC in GCC. Let me actually Google that, what it is exactly called. I think it's called, what it basically does is that every time it does a function call, let me actually take notes so that we can revisit this in the end. So yeah, so the first one that I told you about is basically stack painting. Stack painting technique. The other one is basically like your compiler. And the way your compiler does is that let me quickly Google there what it is called. Um, it's called something like stack protector or stack usage or something like that. Let me stack protector. Yeah, it's called dash f hashtag dash protector. So there's a flag in compiler that you can set up. It's called dash f stack protector dash all. So what it does is that every time it makes a function call, and every time it ends a function call, it adds this small piece of code. What it does is that it 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 takes a look at the stack pointer, um, basically stack pointer when it starts and when it ends a function, and it basically compares if the stack pointer is greater than, sorry, because we have a descending stack pointer over here. So it basically assumes that the stack pointer value is greater than the stack limit. If it's greater than the stack limit, let's assume that this our stack limit is over here, where there's like green. This is our stack limit. And now depending what's, if the stack pointer value is over here or if it's over here, depending on where it is, it would show us if the stack has overflowed or not. So it's a, like, compiler adds it, and based on that, if it is, then it depending on compiler, it can cause an assertion. It can run another function which you can override. It can even trigger a memory, um, like a memory fault. I don't know what GCC does exactly based on that, but I think its behavior could be configurable. And if it's something like an ARM GCC, my understanding is because ARM architecture is standardized, it would trigger a memory fault using 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 the NVIC. Any question about this second approach? Like, how would you do the stack corruption detection, basically? And the third one is basically you can use the one provided by, like, all of the RTOS. They also provide an implementation where this basically because with tasks you provide, like with static tasks, you provide it with the with the memory that's either allocated statically. With static tasks, you provide statically allocated memory. With dynamic tasks, which are created at runtime, you provide memory which is allocated in the memory dynamically. So what it does is that it basically, as part of when it's running, it kind of tracks how much stack you have used. And one of the ways it does is that, let's say that, let me rub this away so that we can make some more pictures. But the basic idea is that you can configure it using free RTOS or other APIs of other RTOS. What it does is that if you allocate, let's say that this is your RAM again, and within that RAM you have allocated this small chunk to this RTOS. Usually what it would do is that when you allocate this, usually at the end, before starting the task, that's one way to do it. There are different approaches to it. It would just choose the last two entry and fill them with, again, it would kind of paint this last two entries with a specific magic number or something like that. And the idea is that after each time you are done uh, running your task, like when it's ready to go into the uh, idle mode, or you're waiting on something, it checks if those guards, they call it guards, stack guards, if they got overwritten. If they got overwritten, then it knows that you have basically touched the boundary of your stack. So it means that your stack is overflowing. That's a very simple way of doing it, but lately they have become much more smarter, and I think they kind of reuse the same thing, they probably, but my understanding is that they can even see how much of the stack are you using. And my understanding is they basically do the same thing. They fill it all up, and intermittently they check how much of it have you used. Like if you have used, let's say, 80%, then I need a smaller, if you have used 80% basically, then only this much would be left, right? Like 20% of this paint would be left, all the other fun would be overwritten. So yeah, so you can use like the RTOS provided stack usage routines, or you can also say like you basically, most of the time it's like you just configure a macro and it becomes enabled automatically, and then you can um, call some other function which either print it, or which raise exception, or which raise false one if the RTOS detects that it has been overflowed. The stack has been overflowed. Any questions with any of these approaches? There's even one more which you can use, and it takes advantage of the hardware memory protection unit. But the thing is that a lot of times those memory protection unit, they are designed against access, um, access like into areas which are not into areas. And the way it's done is that you usually tell that, oh, that the memory or the application can only access something like a memory from a certain zone or certain number of pages. So it is not, it does, you don't have that finite control. You usually can tell it that it shouldn't be able to see like 2 raised to power n bytes. So it would be basically in increments of like 8, 16, 32, 64, like that. So you cannot say like, oh, these, if you have provided a stack of like 800 bytes, you cannot tell it that, oh, you see if someone accessed memory space after these 800 bytes. you would only be able to set something like 512 or 1024. There, because the idea behind them is not to detect stack overflow, it's more to see if or prevent us memory usage or memory access beyond a certain area. So like you can configure it so that your RTOS has access to the whole stack or the whole RAM. Or your RTOS has access to a specific part of the memory. Like you can set it so that it can only access this part. RTOS can access this green part, whereas your application can only access this part on the top. And yeah, these are some of the ways that you can set it up. It's more designed for like security and like to kind of disable access to certain areas of the memory um as opposed to like stack overflow usage detection. Any questions?
I have a quick question on the stack painting. So,
Mhm.
I assume for the stack painting, you don't have a guide that differentiate which portion is for the stack and which portion for the heap, right? So, but then you paint everything, and once a heap bypassed a heap, that's how you know the stack corruption has taken place. Is is that how the stack painting works?
So yeah, why not let's just repaint it. So to answer your question, how would you know whether if the stack if you have, let's say that we started off with green paint, or which is like a magic number, right? And we painted all of this, right? And application started using it from the top. Let me also erase this so that you can see what my point is. Um, right? Something like that. So you have painted your whole RAM or your whole stack space basically with this, and then you start the application. Application starts initializing its variables. And when it starts initializing variables, it uses this space, it uses this space, it starts using this space, because each new function call and each new function variable within that function, it's basically incrementing the stack pointer, and it's using that space for calculations, for storing data, for doing reads and writes, and it's like getting all of these green paint is basically getting overwritten, right? So at and then intermittently, you basically start looking from this. Let me use zero. You start looking from this, and you see if each let's say your paint was like a 32-byte number. You start seeing if this each 32-byte number is same as that magic number, that paint magic number. And wherever you find the first 32-byte number, which does not correspond to that magic number, you know that that's where your stack uh, has been, like that's the depth of your stack. Does that make sense? Have I answered your question?
Yes, I think I misunderstood just now that I thought the whole thing that you painted was including heap and stack. So I believe the stack painting is just painting the whole stack, and from there you see what are the returns and what is the magic number, and does this fully overwritten or not, right?
Yeah, basically that's the idea, that you basically you know where the heap ends, and basically from there onwards you start. So you can paint wherever you want to paint, right? Like you can paint the whole RAM, and then but you have to know where the heap ends, and that's where stack painting is a little bit not useful, because then you also need to track where the heap starts, where the heap ends. So that makes it very tricky. But to answer your question, yes, we do need to know where the heap ends. Otherwise, like let me show you. Like if for instance, when we started, we had painted the whole RAM, and then we started allocating memory. It was used over here, it was used over here, some of it was used over here, some of it was used over here. Now, and then you freed that memory. What would happen is that that memory would be freed. Like your allocator would see that, oh, I have only used this much memory, like it would point to over here, but before it freed that memory, it did use this part, right? It did use this part over here. So so what it makes it tricky. But with memory allocator, it's much more easier, because every time you allocate a memory, your malloc is getting called, and you can override the malloc. And another thing you can do is, like, you can, that pointer that's returned by the malloc, you can use that to know, you can use that to update the heap limit. So every time you call malloc, you can basically say like malloc, you can say like app malloc, and that app malloc basically um it knows that, okay, this much memory was requested from me and this pointer was returned, so it can very easily say that the last time the heap, the malloc or this memory was allocated, it was the memory that was returned plus this number of bytes. Does that make sense?
Yes, thank you.